Okay, so welcome back, everyone. Professor Panigrahi is a leading expert in quantum computational field theory and data analysis through wavelet transforms. He has earned his PhD from the University of Rochester, USA, and he has held prestigious academic and research positions at the University of Illinois, University of Montreal, University of Hyderabad, and Physical Research Laboratory, Ahmedabad. He currently serves as professor and dean of faculty at the Indian Institute of Science Education and Research, Kolkata. His pioneering contributions have significantly advanced the experimental and algorithmic framework of quantum information processing, including demonstrations using IBM's quantum computers. He has also contributed significantly to entanglement-based protocols, quantum gates, and quantum algorithms. So Professor Panigrahi is also a fellow of the National Academy of Sciences and Gujarat Science Academy, and he continues to be a mentor to and inspire emerging researchers across the globe. So please join me in warmly welcoming Professor Prasanta K Panigrahi for this concluding session for today. Sir, the floor is yours, sir. Sir, can you hear me, sir?
Yeah, I can hear you. Just give me a minute. I'll just already it is.
Oh, okay, sir, yes.
Is it visible? Hello?
No, sir, it's not visible, sir.
Hmm. Oh, serious. That's what. Yeah.
It is visible, sir, now. We can see your screen.
Yeah. Just 1 second. It will go on.
Who's already sharing this? No, he's sharing the wrong one. He's sharing the wrong one. That is okay.
That's the one.
Why is it not showing?
Yeah.
Are you able to see it?
Are you able to see it now?
Yes, sir.
Yeah.
Yeah,
Yes, sir.
Yeah. Okay.
Yes, sir, it is visible.
Okay. Yeah. Wait, 2 minutes. Also, okay. Wait a second. No, how does it? Okay. बंद कर देता हूँ। Yeah, I think it's better now.
This one.
Yeah. Why? It's so cool.
What's that?
Yeah, it's okay. Yeah, so.
Yeah, let's go there. They can see.
Is it whole screen is visible?
Yes, sir. The whole screen is visible, sir.
Okay, but somehow it's not coming from me. Let me see. Okay, so that's fine. I'll say it's okay. Yeah. So thank you again for kind invitation. Now you can imagine that I'm truly a classical physicist because it takes time to load the talks. So today I'll be just giving you an overview of this quantum science and technology. What are the recent developments? And I'll also give you a timeline. You know, all of you have been exposed to quantum mechanics. You guys all are familiar with quantum mechanics. So it is 100 year of quantum mechanics. The question arises: why does it take so long for the quantum mechanics to mature into technology? So bear along with me, because the thing what you need for quantum computation right now is very elementary. So this is quantum science for technology, the recent developments. Now I'll give you overview. Essentially timeline when we started 100 years back, when Heisenberg discovered this matrix mechanics. Next year, Schrodinger gave his wave equation. You can stop me at any point, and then we can discuss, because it's more of introductory kind. Now, what are the basic principles of quantum mechanics that is involved in carrying out quantum computing? Essentially, superposition and entanglement. Since most of you are familiar, already some talks are there, I'll sort of go through it very briefly. Now, qubit is something which are our spin up and spin down states, a two-level system. So essentially, when you go to a quantum computer, you replace 0 and 1, the numbers, by matrices. Okay, so simplest one is this qubit. They are vectors. So therefore, once matrices are there, vectors are there, all the things what we learned from vectors, superposition, and entanglement is little involved structure. Already I could see some of you talks have involved entanglement. I will also elaborate on it. Then I'll go to real quantum computers, where are the building blocks. What are the things, for example, what you need to keep in mind? For example, when you are doing quantum principles, certain things you have to keep in mind. Just in relativity, speed of light is c. You can't go faster than that. Similarly, here there are certain theorems, like for example, a quantum file cannot be xeroxed. If the file is unknown, you cannot just make a copy of it. It was discovered in 1981. As we are moving along, many interesting things are being discovered. And keep in mind that all these things are discovered through very basic ideas. Like for example, quantum mechanics, any process you want to do is through unitary matrices. So using properties of unitary matrices, you can actually rule out certain things which quantum mechanics cannot do. So unitary matrices, keep that in mind. Now, fortunately, quantum computing is fairly easy, because all you need to know is that two matrices, a 2 by 2 matrix and a 4 by 4 matrix. The name is Hadamard and control knot. Now, after this thing gets over, I'll tell you a little bit about my work, a recent work, and that basically involves the foundation, what we learned about the double slit, triple slit experiment. In double slit experiment, we know about wave particle duality, and you will amazed to see that these things are still ruling the roost. Namely, I'll tell you about one recent work which has been experimentally verified, that involves three slit, not double slit, three slit. In double slit, we know about wave particle duality. In three slit, you will find out very interestingly, entanglement comes in, and it has been experimentally verified. I thought I should let you know that how simple things are there, and yet a lot of things are there to play around, and you can literally sit at any part of the world and play around and discover new things. Okay, and then see, for example, Niels Bohr has played a very significant role, and in 1900, Max Planck had this Planck's theory. That is how quantum mechanics came in. Subsequently, there were the old quantum mechanics, hydrogen atom, pretty much in the model of the solar system. Then, subsequently, things developed. 1925, Heisenberg gave rise to his matrix mechanics. Subsequently, Schrodinger came up with Schrodinger equation. One is in terms of matrices, one is in terms of differential equation. Fortunately, both are related, but soon found out that both of them are related. And they are describing the same thing. So non-commutativity from matrices manifests as xp commutator is equal to is bar. And a lot of, then for example, this electrical engineering professor, Dirac, he actually sort of brought in very beautiful, simple structures connecting classical mechanics with quantum mechanics, namely Poisson bracket goes to, commutator. And so the mathematical structure is pretty similar. Poisson brackets satisfies anti-commutativity, that commuting relationship, and x and p Poisson bracket is not equal to 0. Similar kind of thing, it goes over there. So this beautiful structure and analogy between quantum and classical was much emphasized by Dirac, his 1932 book, which sort of deals with double slit experiment and points out that how a single photon can interfere with itself. So please think about it. What is the meaning of a single photon interfering with itself? If you reflect for a moment, you will find out that what is really meaning is that there is a wave which splits into two parts through one window. There are two slits and it interferes. If there are a lot of photons, as we do in classical interference experiment, very quickly we see black, dark, no light, dark, and bright fringes. But if you take only one photon, you will find out after large time of exposure, when you have sufficient number of photons, same picture emerges. So this was basically the thing which people interpreted, probabilistic interpretation of quantum mechanics. So this, this Dirac's book dealing with double slit experiment is worth going through because right now it has become the source for generating quantum random numbers. And as I told you, our simple work dealing with triple slit experiment brought in the surprising result of entanglement. So these things, it throws surprises at you. And quantum mechanics is tricky. So with all these things, this singlet state, if, for example, hydrogen molecule, the 2 electrons are in a singlet state. Helium, the 2 electrons are in a singlet state. So this singlet state is the simplest example of entangled state. And EPR paradox is about that. Singlet and triplet, for example, if you take, both are entangled states, maximally entangled to put it properly. And it's amazing that this state has been there in spectroscopy with us all these years. So what is so big deal about singlet state? Einstein realized, suppose one electron and another electron are in a singlet state. So it's a state which you cannot write as product, up, down, minus, down, or by root 2. You can never write it as product state, unlike up, or down, down. And he sort of imagined that if one electron is in Delhi, other electron in Washington, what will happen? What is argued theoretically, of course, with a, not a singlet state, with a more general continuous variable state, the singlet state analogy to Bohm, that if you measure, see, that is where measurement comes in. For example, Niels Bohr continuously emphasized about the role of measurement, collapse of the wave function, the so-called Copenhagen interpretation, how beautifully it comes here. If you measure, if you find spin up in Delhi, Washington spin will be spin down right away. Up here, down there. If you find down here, it becomes up. How is it that these two guys are communicating? This is a very simple consequence of entangled state, up, down, minus, down, or by root 2 singlet. Only when you imagine that these are physically not in the same location, to be honest, the 2 electrons in case of helium or the hydrogen are actually not in the same location. Their Pauli exclusion principle is there, and they sort of are away from each other. And that distance, for example, if you imagine is very long, you can physically picture that well-known locality comes in. How is it that a measurement in Delhi which collapses the wave function from two terms to only one term? That's two completely probabilistically, up, down, or down, up, we don't know which one. Completely random. In fact, this completely randomness about the measurement has led to random number generator, quantum random number generator. So here, the non-locality idea was due to Einstein and also API paradox. What is this action at distance? Who makes this wave function collapse? Up here, down there, or down here, up here? That has bugged us since then. It famous API paradox has led to technology, and that has led to beautiful experiments. In fact, 2002 Nobel Prize is because of that. So this question, this non-locality of quantum mechanics, people started looking at it seriously. For example, quantum electrodynamics developed during 40s, but the people who are serious, they started looking at it. David Bohm, for example, in 50s, came up with the spin analog of this. So what I'm telling you, the singlet state is because of Bohm. So this Bell, for example, Bell is a particle physicist, as you know, is a field theorist. Professor Sunil Mukhi pointed out about field theory. You can see Bell-Jacob anomaly. Adler-Bell-Jacob anomaly is something which we learn, and very profound things in quantum field theory. Same John Bell in 60s was looking at it, and he pointed out that, look, if it is, he sort of imagined is like a coin tossing game, and he was from UK. So there was a famous statistician named Boole, Boole. So Boole has actually analyzed cricket match that two umpires throwing coins, and he looked at a combination of whose outcome would be head, 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 tail, tail, head, and tail, tail. And he took a combination which sort of pointed out this probability of this thing can range between 2 and -2. You can imagine if it's up, up, then it's 2, down, down will be -2, up, down, and minus down, up will be like 1 minus 1, which will be like 0, 2 to -2. Very simple. But you look at, Wikipedia, look at Boole's identity. A lot of interesting consequences are there. So John Bell imagined the same kind of thing. First of all, what are these analog of two outcomes? Well, polymatrices, sigma x, sigma y, sigma z, and eigenvalues are 1 and -1. These are operators. So if you measure a state and it collapses, there's a probability. For example, imagine a superposition of up and down. If you measure up will be 50%, down will be 50%. 1 and -1. It's like coin tossing. So imagine that. Then he took this operator, polymatrices combination. You have to do two measurements. So product of two polymatrices suitably organized. If you look at it, there are 4 terms, 3 positive, 1 negative, and it's sort of nicely factorized that if it's up or down, it will be 0, up, up, down, down kind of thing will give you 2 and -2. When the state is separable. So it matches with Boole's idea about this statistics in case of cricket match with quantum mechanics. Separable states 2 and -2. Lo and behold, when you took this entangled state, up, down, minus down by √2, or up, 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 down, flop, down by √2, similar to a triplet, you got 2 √2. Big surprise. That means if quantum mechanics is correct, it is different from classical mechanics. Classical mechanics values for this simple experiment through correlated observations of spin can go between 2 and -2. Quantum will go to 2 √2 to -2. Now this aspect has been now used to put devices in the quantum domain so that if somebody tries to see, then security will be assured because the quantum principle comes in, eavesdropping can be detected. So this business, tuning a quantum apparatus so that it stays between 2 to √2 brings the quantum effect. So a lot of interesting things you can do using this. This is a very simple observation. Happens in an entangled state alone. Separable state is same as classical 2 to -2, whereas quantum is 2 √2 to -2. This one was later verified in optics experiments, and led to a bit of more general ones, CHHS inequality, Koster, Horn, those 4 authors. And in 80s particularly, Aspect, Zeilinger, Clauser, and all these people through optics experiment verified it. So this verification followed some kind of correlated statistics. What you observe, you take, for example, you people are familiar to particle physics, I could see that. If you take a pi naught meson, it decays two photons. Two photons polarization, if you see, actually they're correlated. And this correlation is such that, like up, down, minus, down, up by root 2 kind of correlation. If one photon spin is polarization is one direction, other will be opposite. So you can check that these two photons, because of the angular momentum conservation, come out in spin zero, and they are correlated exactly in the manner what I'm talking about. So you go to both the ends. One could be in Delhi, one could be in Washington. Start measuring. So point is that you have to do a correlation kind of measurement. Up here, up will be up there. Down here will be down there. Or whatever your state is. Up, if it is up, down, minus, down, up, then it is up here, down there. If it is down here, up there. So this kind of measurement was done. And they indeed found that it is correct that this correlation survives. And the factor is between 2 to 2 root 2. Perfectly entangled state. That is how it was verified that quantum mechanics is intrinsically non-local, yet it is correct. Whatever you predict, that answer comes out. So this is the key fact. Very simple spin measurement involving two parties on a simple quantum mechanical state like a doublet, a singlet or triplet. And if you take up, up or down, down, separable state, it is between 2 to minus 2. And this triplet and singlet, 2 root 2 minus 2 root 2. So it is perfectly non-local. The moment you measure here, the state will collapse on the other side. But one thing to remind you, it is not instantaneous. It takes velocity of light, as we learned from relativity. No effect can propagate faster than light. So that has led to more profound things. Some of you should think about it. Information velocity cannot go faster than light. So two principles. No unknown file can be copied in quantum world. Information cannot go faster than light. So very good. So now, all right. So now this is the experiment these are the EPR paradox I was mentioning. John Bell, 1964. You can sort of look up his works. Simple, deals with only polymatrices. So then what happened in 60s, the people started using computers. As you know, for example, von Neumann made the computer. After it was released from quote unquote the work of the war, namely design of the nuclear bomb, people started using it. Fermi passed Ulam, that model was tested there. And then people started using it, computer became smaller and smaller. For example, in 60s, Gordon Moore came up with this thing that computer size is up every 18 months becoming roughly half. Namely, you can actually put in more number of transistors in an IC, integrated circuit every 2 years, so 18 months roughly. So then what happened is that because your computer size became smaller, heating started. A lot of heating, people try to understand what is this heating. Heating means thermodynamics. So now, where is that paper? Thermodynamics. So then you will find out that this business, people started understanding thermodynamics more carefully. I have probably kept that reference somewhere. It was Landauer who pointed out 61 paper, very beautiful paper. Loss of quantum information leads to heating. How much of heating? He found out one bit of information loss is half kT energy. 1 bit of loss is half kT energy. You may ask, what is this bit business? Remember that by the time Shannon's channel capacity had come, so the C bit, in terms of 0, 1, 1, 0, for example, if when you send information, what is information? Information is variation. If you have only zeros or all only ones, there is no information. So because of Shannon's work, they knew about information, and classical bit has been defined to send messages. Channel capacity has been found out. Same thing they found, 1 C-bit of information loss is half kT amount of energy. Beautiful paper was 1961 physical review by Landauer. So heating business brought in thermodynamics, statistical mechanics, quantum mechanics, computers together. So then in the 70s, same picture went on. People try to understand. Then there was this person called Toffoli. I'll show you his gate. They're doing, designing gates in a regular classical computer. He pointed out that, look, I have a gate where there is no heating. It was Feynman who realized that that is because this object is a unitary matrix. In fact, people have used it. So then he came up with this thing that you can actually sort of design a quantum computer. Of course, he had in mind to solve the problem of, this our confinement, quantum confinement, namely quarks are confined inside a proton. So this confinement problem in QCD is what he wanted. So in the 80s, he solved this confinement problem on the planar electrodynamics. But he wanted a real world. So he found out that these kind of problems are difficult to attack. If you can make a quantum for a computer using quantum principles, then you will be able to solve these kind of problems. So that was in 80s, paper nobody was accepting. Fortunately, it got published in IJTP, International Journal of Theoretical Physics, worth reading the paper. So development started at that time. But remember that in between all these things, this wave particle duality has played a key role. So after 1982, it was David Joyce who sort of pointed out in a more concrete way that you can actually do quantum computing and design a quantum Turing machine. So he came up with these very simple matrices. And then a lot of development took place. Major development I'm listing 1985, David Joyce development of quantum Turing machine. Then Peter Shor, 1994. Peter Shor pointed out that you can use quantum computer, precisely quantum parallelism, to solve real world problem. What is the real world problem? Factorization. If you see, for example, in papers in Nature, I was, in 93, I joined University of Hyderabad. Later on, people were, using NMR machines to do quantum computation. You can see Nature papers, 21 is equal to 7 times 3. So you may ask, what is the big deal? It was basically used to show that a quantum computer can be used to factorize numbers. What is so great thing about Peter Shor's thing? His point is that essentially showed that exponential thing and polynomial thing. What is exponential? What is polynomial? Computer science people, for example, have their way of dealing with numbers. They found out that this factorization problem becomes very complicated. You need exponential time to solve it. But quantum computer can use it, so-called polynomial time. Polynomial time is solvable. You can do it. So that was it. We must ask what principle of quantum mechanics allows it? Superposition. Superposition like parallel processing. Quantum parallel processing allows you multiple hands. Using that, you can do the problem easily in polynomial time. So these terms are also new to me, polynomial time, exponential time. And for example, quantum computer, what are the problems which are unsolved problems that you have to talk to them? We physics people don't know. We have our own problems like the confinement problem, varieties of things, finding round state for many quantum systems, solving high TCs for conductivity. Similarly, computer science people have their own problems. You talk to them and become a friend, and any of those problems you can crack, you become world famous. Then comes Grover, 1997, very beautiful paper, Love Grover. He finds out that you can use it as a source algorithm. Very simple. I suggest that please take a look at it. Very readable. Source paper may be a little difficult, but Grover's paper is very readable. All it does, you can take a matrix analog, take a column vector with all entries as 1. Now you ask yourself, if I want to sort for one fellow, which is first one, plus 1, all zeros. So the sort state you are looking for is one of them. Equal superposition of that has been given to you. How many steps for you it will take to find it? You can convince yourself. For example, it will take fairly long, roughly n square amount of time to do it. But Grover said that you can actually do it much faster, order root n. And if you really look at it, it's a very simple thing. Even now also, I really get fascinated how he did it. He uses 2 operations. One is called parity. What it does not do anything to the state you are looking for. All the others are multiplied by minus sign. So you mirror reflection around the state you are looking for. Then again, you add the whole thing again. If you add the whole thing, what will happen? Everything will become less because plus minus will cancel. Only the fellow which you are looking for, because the sign is not changed, that will keep on adding. If you do repeatedly, very quickly that state will come out of the background. You can detect it probabilistically. That was his idea. Two simple operations, including using wave function, what you are looking for, let's call it phi, and what has been given to you, let us call it psi. Two operators. Please take it out. Even now also it is fascinating to see this. One is identity minus 2 times phi phi. Another is identity minus 2 times psi psi. You repeatedly apply, you will find out state you are looking for very quickly will emerge from the background. And that is so simple. People have actually searched, use it for searching. Many people believe nature makes fundamental use of this thing. For example, like photosynthesis. It's a very, very simple, beautiful algorithm. Grover's search algorithm. Can be used in many, many places. Source paper is a bit difficult to read, but I am not discouraging you. Uses Fourier transform, quantum Fourier transform, and measurement, okay, to do factorization. And of course, after that, so-called Chinese remainder theorem, two part to it. Okay. So then bit of timeline. So as I pointed out to you, it was this 1982 experiment. And these are the, so after that thing, people started talking about quantum. For example, this Bennett and Brassard was from University of Montreal, where I was a postdoc, electrical engineering department. Bennett was from, IBM. So they're in Bangalore. They heard this collapse of the state by measurement. That's what I have been told by Bennett himself. They say, oh, that's very nice. So, for example, if I send information through photons or quantum particles, if somebody will see it, the state will collapse. So I can detect if. So that is how over a glass of beer or a pitcher of beer, Bangalore BB84 algorithm came out. Bennett Brassard 84. And, for example, Bennett visits India very regularly. Last year also he was here. Now, this one is a very simple one. Use a single photon and measurement. Pretty readable. I suggest that people please take a look at it. People are implementing it experimentally. Basically, measurement and basis. So, for example, spin, you want to measure it using spin along the z direction 1001 or along x direction, which is 1 by root 2 1 1 1 by root 2 1 minus 1, or along y direction, which is 1 by root 2 1 I 1 by root 2 1 minus I. Which basis? Is it 45-degree polarization, linear polarization, or circular polarization? So basis makes a big difference. So they pointed out that this fact that collapse of the state and the basis which you are measuring, it depends on that, can be very effectively used to detect if and to generate a key. What is a key? Set of numbers 0 1 1 1 1 0, for example, which is secure, which you can use for in exchange of information between two trusted parties, Alice and Bob. So please check it out. Very simple. Only uses this fact that measurement is to collapse of the state. Now, which basis you are using? For example, if your state is along z direction, if you measure along z direction, nothing will happen. So if the basis of measurement and the state itself coincide, nothing will happen. State will remain unchanged. If they don't coincide, for example, if the state is along x direction, which is superposition of 0 plus 1 by root 2, if you measure it using 0 and 1 basis, the state will collapse to either 0 or 1. This is used to generate random numbers, okay? And that is the idea which was used for single photon measurement basis for BB84. Now, many people have implemented it. Machines are available, okay? So then, for example, then came the idea of quantum teleportation. Very beautiful idea. If some of you are interested, maybe somebody will work it out for the blackboard for you. What you do is you take this singlet or triplet state between Alice and Bob, an unknown state psi at the end of Alice. Alice does the so-called Bell measurement, two-particle measurement. Then classically communicates the result to Bob. The moment she does this Bell measurement, what happens is this unknown state psi gets into the channel. Alice and Bob are entangled. After that, entanglement is destroyed between Alice and Bob. Alice gets entangled with this unknown fellow. But in the process, this information that the unknown state is made out of alpha 0 plus beta 1, alpha beta, gets transmitted to Bob. Once Alice calls up Bob, Bob does some amount of local twisting, little bit of local unitary transform. What is local? It can be done only at the end of Bob. Measurement, initial measurement was done only at the end of Alice. The measurements are local measurement. So then over a telephone channel called classical communication, Alice tells Bob, do this, do that, and Bob recovers the number alpha beta to reconstruct the unknown state. Imagine it's such a beautiful algorithm. A unknown state goes from some location like Delhi to Washington. Nobody knows. Alice does not know what the state. Bob does not know what the state he got. Channel doesn't know. But the state does not go. It is the numbers which go reproduce the state at the end of Bob. In the process, local measurement has been used. Measurement at the end of Alice, measurement at the end of Bob. Some unit transformations have been done. Unit transformation and the channel that is used is the maximally entanglement channel, like a triplet or a singlet. So very beautiful. It will teach you a hell a lot of things. For example, what the meaning of measurement, what the meaning of single particle measurement and Bell measurement, what are the Bell state basis, how, for example, an fully maximally entangled state between Alice and Bob, after the unknown state psi gets in the channel, decouples completely. So this has led to entanglement monogamy. It was discovered that the entanglement is actually like monogamous nature of quote unquote animals or human beings. If two particles are maximally entangled, if the two electrons are in a singlet or double state, a third electron cannot get in. If somehow you force it in, then what will happen is that that electron will come out of that entanglement, it will completely decouple and join up with this flow. So imagine Alice, Bob, and Charlie. If Alice and Bob are maximally entangled, Charlie cannot get in. The moment Charlie gets in, Bob and Charlie get entangled, Alice is out. This kind of scenario is called entanglement monogamy. It was discovered little later, but this teleportation uses this fact. Okay, very beautiful thing. Experimentally, people have seen it. For example, 1997, then actually recreate state at some other end, completely not knowing what the state is. And the party who discovered it, reconstructs it, also does not know what the state. And the state information has gone alpha beta from one end to other after a classical communication, namely telephone call, and completely without any mistake. Alpha does not become alpha plus 0.1. So if it is successful, complete information goes from this into that. Remarkable. And again, speed of light, not faster than speed of light. That took a lot of understanding how information velocity cannot exceed velocity of light. Okay, so beautiful. So now, okay, so since 90s, late 2000, things move very fast. Lot of experiments, things came up. For example, by 2015-14, China has taken a huge lead. They have huge optical fibers. They have quantum satellites. There are beautiful experiments done, for example, in Vienna and other places, in France, US also, showing long distance quantum teleportation. For example, so now this satellite, Messias satellite, is a quantum satellite. Huge between ground stations, large distances have been covered where quantum information can be sent. Then came, for example, IBM with its quantum computer. Google has now two chips, one is Sycamore and recently something else. The claim is that quantum can do things faster in some cases as compared to classical. But let me tell you that, for example, except Peter Shor or Grover Schwarz, other things are not completely well established yet. You find out that today some claim has been there, but very quickly people find a classical computer with a smart algorithm can do the sensing better. So don't give up on classical algorithms yet. They're quite powerful. They also are very robust against noise because they use 0 and 1. Quantum is very noisy. That we could. So most likely some kind of a hybrid mechanism would be probably better. So now, for example, DST has National Quantum Mission has called for algorithm development today. Please take a look at it. And AICT is also developing courses for BTech engineers. Again, that has just come out. They have selected people who will write books. They have selected people who will review them. So quantum computing, quantum algorithm, all these things are now pretty much going into syllabus. And fortunately, because of National Quantum Mission, now there are 4 hubs, 4 areas: quantum materials, quantum communication, quantum algorithm or quantum computing, and then what is the other one? Quantum sensing. Because So out of that, communication has gone far ahead. Now, many of our experimental people, like for example, Delhi IIT, PRL, and you know, RRI Bangalore, many places, people have shown quantum telephone, QKD, quantum key distribution using light. But beyond that, entangled photons people have produced. People have also used it for QKD, quantum key distribution. But much more application will follow because entangled photons can be used for imaging, something called ghost imaging, like Anton Zeilinger has shown. So much more useful things can come. And device independence. You can do something where nobody will know what you are computing. Very powerful applications are yet to follow. And this algorithm, please keep in mind, quantum algorithm is something where we can make a tremendous contribution because we Indians have a aptitude, which is very suitable for algorithms. So this advertisement which has come today, National Quantum Mission in the DST, please take advantage of it. Okay, so how are you doing? For example, in terms of this thing, you will find out this is a report 2019. I have not modified it yet. 2021, similar kind of thing. Actually, India is doing fairly well. That in India, large number of quantum trained talent is available. You may ask, why is it? How is it possible? And in fact, if you see absolute numbers, India is the largest. If you remove UK, European Union is lower, and this was also picture 2021. You may ask, how is it possible? Because you see, Indian students actually learn from each other. IBM has been conducting, these workshops quite systematically. They have quantum simulators available. Many of our students, they do project and play with IBM quantum computer, take courses and pick up quantum computing and relevant courses, which shows the interest and up to dateness of our Indian students. So now, for example, you may ask, what kind of problems one can attempt? I am an outsider. Can I do something meaningful? Answer is yes. For example, I'll show you a computer scientist named Urmila Mohadev. You can search in the internet. So she basically asked the question that how do you verify? If somebody says, I have a quantum computer, how do you verify? Quantum verification problem. You can check. She was a PhD student of Umesh Vazirani in Berkeley. 8 years, one paper. It came because there was a quantum computer developed in Canada called D-Wave quantum computer. Nobody believed that it's a really quantum computer. You believe that it has some coherence, but not exactly quantum. But thanks to her work, more or less, she is accepted that it's a quantum computer. 8 years, one paper. Now she's a faculty in Caltech. Now, similarly, if you think that you don't know much, here is an example I give it to my students. This young girl, she was 18 years. When was that? 2018 or something. He came to do a small project with a professor in the University of Texas. So she was told that here I have a matrix like Sudoku. Some numbers are missing. Can you fill it up? And fill it up, very fast. But with two conditions. Condition one, that most of the elements are non-zero, non-sparse. So simple is good. If it's non-zero, then I have to fill the less. I can really find it out. Non-sparse matrix, which is very favorable. And then second, low rank. Low rank means what? Means that some of the rows or columns are dependent on each other. Not everything is really independent. So very good. So she used a standard algorithm, developed it on her own, and so that you can actually solve it in polynomial time and quite fast. In fact, there was the professor release showed that these people from MIT, Seth Lloyd and others, they have used something called quantum singular value decomposition to show that there is a huge quantum advantage. Quantum computer can do it faster than a classical computer. In what she showed, that there is nothing of this quantum speed up. Okay, and you can do it in a classical thing. It's called quantum recombination problem as fast as a quantum computer. So therefore, when somebody says there is a quantum advantage, people look at it very carefully. Is it really there or not? And at that time, she was 18. Not much of quantum mechanics, because to do these things, all you need is matrices and clever use of measurement. Measurement leads to collapse of the state. You can read about her. That paper is, I think, published. Now she is doing her PhD or might have just completed her PhD. very nice thing to read about. That whenever there is a quantum speed up, people question, and anybody can question. If a high school student can do it, why can't we? All right. So now many things are DRDO has doing nice things. In Delhi, they have put up a recent lab. The products are beginning to come out. ISRO also is showing free-space quantum communication. Now, recently, for example, we heard ISRO is putting up a quantum satellite soon. For example, PRL, that's Professor R.P. Singh and group, where I was in the beginning. This Center for Quantum Optics and Quantum Information came up during Professor Agarwal's time. I was the first division head. Same thing has led to this entangled photon, single photon sources, Professor R.P. Singh in PRL and Gautam Biswas. Now they have shown how to do free space quantum communication, quantum key distribution. And this thing has become technology now. It has gone to space application center SAC in Ahmedabad. And apparently a satellite is going to come up. You see, so therefore, this was, I can tell you, I was there 2002 to 2007. Quantum optics, quantum information was the first thing that came up there. Professor Agarwal was a visionary. Girish Saran Agarwal, one of the leading researchers in his domain, now in Texas. So he foresaw that quantum technology is going to make a mark. And that's how this whole thing started. Now, it has become a technology to the extent that satellites are going to put up this year of the quantum. So therefore, and if you again ask, the principles that are used are very simple ones. For example, measurement and the idea of matrices. Therefore, anybody who is interested in it can make a difference, particularly outsiders, because physics people, we know too much of quantum mechanics. Now, for example, people have come up with the creative ways of doing research. There are 6 universities in Sydney. They have joined together, gotten some grant from the institute, from the government. They're running a quantum network. All these trains, buses are running through quantum computer communication channel and running efficiently. So for no accident, they have got money for research, and a lot of you can check out. Large number of PhD students are there. In fact, from my group in ICR Kolkata, at least 15 students have gone there and joined in the PhD program. They have experiment, theory, many things. So now many cities are using quantum communication channel because it's secure, and you can check that this quantum communication has come to stay because it is secure. I was told that almost all these things, communication now in government channels are through this kind of quantum messages. And check, there are approved startups. One of them is QNew, Bangalore, and CDOT also. They have come up with quantum communication devices, fairly simple ones, available in the market, not very expensive. So if you want secret communication, you can use them. It has come to stay. That technology has matured. Okay. Now, for example, people are actually coming up with better ideas, like, for example, communicating between a station somewhere and drones, controlling the drones, and in a project people are carrying out, like, for example, SIDAC Pune. So many other applications are coming up, basically communication based. Okay. So what are these things which quantum computer uses? Quantum computer uses simple ideas like superposition and entanglement. And who are the elements who play key role there? Supposedly electrons, atoms, but they're too small. Instead, you take, for example, quantum dot, which is like a big quantum molecule, or superconducting qubit, which can be at low temperature, but still macroscopic. You can handle them. Okay. So it uses, for example, superposition entanglement, then wave particle duality to accomplish what you want to do. What is the superposition allow you to do? It allows you multiple hands. Okay. Parallel processing. So superposition is parallel processing. And then, of course, entanglement is doing this non-local correlation, which is useful for quantum tasks like teleportation and many things. Entanglement is still mysterious. Why, for example, maximum entanglement is responsible for teleportation, not less than that, is something which you should also think about it. At a simpler level, it looks like a matrix factorization problem. But why is it that maximally entangled states are so important? Think about it carefully. And is it always necessary that they are very important? Certain things they cannot do where other people can do. See, for example, is Hardy's There's some kind of a RD game or something, which a maximal entangled state cannot do, but less entangled state can do. So entanglement is something people are trying to understand. Okay. Now what are qubit? Basically, two-level system. Two-level system of a atom. Anywhere you find a two-level system. So pictorially, atom, for example, there are two nucleuses there, two states. Okay, that's it. So, or you can anywhere you can imagine a two-level system. Denote them as 0 and 1. Could be spin, could be polarization. You have a qubit. Essentially, you need matrices. Now, what kind of technology people have realized? IBM superconducting qubit, quantum dot, trapped ions. Those machines are available now. Light photonic qubits for quantum communication. Defect-based qubits, for example, nitrogen defecting diamond for sensing. Topological qubits, which are robust. Like, for example, you see Marona fermions, Marona chip for Microsoft. These are the kind of things. NMR, people have used it from quite some time. It is very mature, but you can extend it beyond some 8 or 9 or 10 particles. But many of these things have been demonstrated using NMR. What is the basic principle? Superposition. Alpha 0 plus beta 1 like vector addition. And the wave is normalized. So alpha mod square plus beta mod square is equal to 1. So now, so this means superposition is counterintuitive. It means that when you measure, superposed state is going to collapse to one of them. Okay. So very important property is like a double layer potential. Your particle can be localized in any of the wells, and which you call it tunneling. Okay. So how do you create superposition? You use light, for example, create 0 plus 1 by root 2. So you create or a double layer potential. Superposition you have to create. Matrices, what will do? Hadamard matrix will create superposition. Okay. Now entanglement is something which is mysterious. Started bothering Einstein, and the TPR paradox came. We people, physics people have been talking about paradoxes, but fortunately computer science people used it. They used it for teleportation and many other tasks. So basically, non-locality is the thing that quantum mechanics is intrinsically non-local. But it works according to what the theory predicts. So, and superposition is again counterintuitive. In a double well, you can imagine the particle can be in this well or that well. So it has led to Schrodinger's cat paradox and many things. It can exist. Yeah. The entanglement, singlet state is classic example. Singlet, triplet, others are there. As I told you in the very beginning, this kind of experiment one has to do. A part source decays, produces two photons. For example, the example which I have taken is, let's say, up plus down down. So therefore, if you measure, the state will be up or down down. Therefore, if Alice is up, Bob will be down, up. If Alice is down, Bob will be down. So you have to do a coincidence measurement that after in a distant lab, if Alice end produces up, Bob, is he producing up or not? If the state is XX and YY, or if it is, for example, XY, YX, which is, for example, up, down, down, or is it up, down, plus down, up? Accordingly, you have to do this kind of coincidence measurement. These are the kind of experiments which are done to verify that quantum mechanics is non-local. Now, what are the companies which are now in the market? Many of them, D-Wave started in Canada, because of which, this Urmila Mahadev led to quantum verification problem. Now, IBM has been a big player. They are building a quantum computer in Hyderabad, Amaravati. They have 150 qubit kind of thing, big IBM centers available. Initially, they are giving access to us, noisy quantum computer, but they have apparently good ones. Many of them have Rigetti, IBM, they have their own simulators which you can play around. Now, many of them are open to collaboration also. For example, if you see Amazon Web Service allows through government of India funding access to many of the quantum computers which you can use. IonQ is a European origin one, uses ions to quantum computing. So there are many companies now and products are there. Quantum communication, as I told you, is a mature technology. Products are available. These people are talking about real quantum computer, which is also coming up and has been made access to researchers now. How does it look like? It has a quantum brain processing unit. Basically, a single qubit is there, and it is protected in a cold refrigerator, liquid helium. and there are optical fibers connecting them so that they can talk to each other. Okay, so when you are sitting here at home, through cloud, you give instruction. That's how it goes. It goes through optical fiber. The instruction goes, and it gives you to the quantum computer to do the task what you want. In fact, you can do that sitting here using IBM or one of the quantum computers. So they pretty much look like pretty big machine. What are the basic principles? Matrix operation. There are two basic matrix operations called quantum gate. One gate creates superposition, Hadamard gate. They're pretty much like classical gates. You could represent them as matrices. And they have to be unitary matrices. Anything quantum is unitary. They are called quantum logic gates, and they have to be unitary. So now, another thing what you need to know is measurement. Measurement will lead to collapse of state and irreversible process. You can't bring it back. But it has its own use. You can actually use measurement to detect if measurement can be used to come up with a paradigm for quantum computing called measurement-based quantum computing. That is not there in the classical world, but possible in the quantum world. So measurement, don't rule it out. Measurement is very useful. How does the Hadamard look like? Hadamard is a matrix, 1 by root 2, 1, 1, minus 1, rotation. It rotates 0 to 0 plus 1 by root 2, 1 to 0 minus 1 by root 2. 45 degree. Linear polarization becomes 45 degree polarization. Okay, and that's all. So it produces superposition. If it is superposition, you have multiple hands are available. But if you use the basis, measurement basis 0 or 1, Hadamard basis will collapse to 0 or 1. Okay, now, so this is one Hadamard. As you know, this matrix was initially used by Hadamard long time back for something else. The other thing is control lot. Here you see who is controlling whom. Bob is controlling Alice. B is Bob, A is Alice. What is the meaning of controlling? If Bob is 1, Alice is going to change. If Bob is 0, Alice is not going to change. You see, second one, white one. Bob is 1, so Alice is becoming 1. If Bob is 1, Alice is 1 is becoming 0. When Bob is 1, Alice is going to change. So physically, it's not easy to implement this. That is the reason why it took a lot of time. Control not. Negation in a control manner. Only if it 1 becomes this. Very good. As I told you, long time back in 70s, Toffoli pointed out that he can design a gate which does things without heating. Very good. It was used in fact in circuits. Nowadays, it is called control not. If Bob and Sally are 1, 1, Alice is going to change. Check it out, the truth table. See that white flow. Wherever Bob is 1, 1, Bob and Sally, Alice will change from 0 to 1. If it is 1, 1, 1, it will become 1, 1, 0. That's it. These, amazingly, if you think about it, these two simple operations, namely control not and Hadamard, is used to do everything. They are universal quantum gates. Everything can be done using them. That's quite remarkable. So universal quantum computer can be designed. But of course, if you want, you can use other things to simplify the calculation, to do it faster and using less circuit because it costs energy to put up bigger circuit. But those two are the universal gates, control not and Hadamard. Can do anything for you. What are they available? Annealing based quantum computers are available. Then you can have, for example, digital ones like 0 and 1. Or again, for example, you can have continuous wave to light. If you are beginning to work on through light, for example, continuous waves. But the ones which are available in the market, a lot of research is going on, are the ones which are based on qubit matrices, simple matrices. Okay, so now there's a gate-based one and there is one annular. What is annular? In annular, you take a quantum Hamiltonian, you take the state, somehow you load your problem into the Hamiltonian, let it evolve. As it evolves, it literally solves your problem. See, for example, you may ask, how does it really work? You see, you take 92 electrons, 92 protons, and some neutrons, put them together. After some time, if you pull it down, you will find that it will become uranium. What does it mean? It means that this complicated problem of 92 electrons repelling each other, attracted towards 92 protons, protons repelling, actually nature solves it to produce the answer of uranium atom. whose levels is the answer you are looking for. So therefore, if you take a problem, somehow can put it in Hamiltonian, evolve it, pull it down, the ground state will give you the answer. And check out with factorization. It really works. That is how D wave works. For example, so other is gate based. You map your problem, convert it into circuit, hard one controller, solve your problem. There are many papers which can tell you how to use gate-based quantum computers or the other one. But main point that they are universal. You can use two gates to do everything. Nothing is left. Now this Bell state has played a key role as I pointed out from the very beginning. So my life started with Bell state and how to do this Bell state measurement. Particularly, you don't want to destroy it. I'll show you why we got into that problem. But remember, play around with Bell state. Even now also, whenever I look at it, I get still fascinated. Why is it maximal entangled? What is the matrix property? That has gave me a lot of insight. For example, my first insight came, I'll show you later, through a student from IIT Guwahati, Vineet Bhaskara. We actually showed that entanglement is nothing but area between two vectors. That came by asking this question, what is so great deal about Bell state? And that you can actually use to show that entanglement is a geometric property. It is actually area between vectors. And to show that, we used this Lagrange Brahmagupta triangle inequality. In fact, we thought it is Lagrange triangle inequality, but therefore later on pointed out that Brahmagupta did it. So Brahmagupta and Lagrange identity triangle inequality, which gave us that result. So entanglement is an area, and it looks and came about by looking at the Bell state more carefully. Maximally entangled state. So how do you prepare it? Use Harman controller. This kind of circuit you can see in IBM. You can drop and drag, take 0, go on to IBM quantum computer. Somebody will maybe illustrate you in the evening. You can create these kind of things. Best place to play around is one of the simulators. The Getty or IBM. You create them. What are the, all the 4 states can be created. They are maximally entangled state. As I mentioned to you, Bell actually showed that 2√2 kind of thing using these states. Now, these are pure states. Then there is, how do you know that this maximal entangled? There then comes the concept of reduced density matrix. What you find is that, when you look at light, we have been told the light can exist purely polarized light. There the Bloch sphere, Poincare sphere, then partially polarized light, which are like a solid ball, totally unpolarized light, which is the origin. So using a solid ball, you can describe all the polarization states of light. Fully polarized, any state, partially polarized, and unpolarized completely. Same thing is like mixed state. Mixed state, a pure quantum mechanical wave function, or this partially polarized, that kind of thing what you describe, partially polarized light, mixed state. Amazingly, what happens is if you take two particle state, if they're maximally entangled, if you look at this one half of it without looking at the other, which is called reduced density matrix, Alice and Bob, you don't look at Bob, only look at Alice. That is called reduced density matrix. What you do is you trace out the other fellow. Then you find because of that entanglement, because these guys are connected, Alice state is no longer pure, it becomes mixed. And that leads to entropy, so-called von Neumann entropy. Using von Neumann entropy, you can actually quantify entanglement. And in fact, Bell states are maximally entangled. As I told you that in fact we found out, thanks to Vineet Bhaskara from IIT Guwahati, that entanglement is actually area between two vectors. If time permits, I'll show you. Another useful state is Greenberg or Horn-Geisinger state, very useful 3-particle state, discovered in 1989. And many of these concepts in quantum mechanics has been illustrated using it. So, for example, how do you create it? Same thing, 3-qubit, 0, 0, 0, Hadamard, controller. It creates for you these kind of states. Very simple, very useful. Now, one task, as I told you, quantum teleportation. If you find some time, ask somebody to work it out on the blackboard, you will find out that teleportation is something which will illustrate a lot of things. The role of quantum measurement, this maximal correlation, entanglement, and how local measurement of two types, single particle measurement and Bell measurement, Now, what the role of basis in that kind of measurement? And then classical communication, what kind of role it plays. So then you will find out very beautifully that you can create unknown states at some other point of your choice without knowing what state you are sending, and the party who is also receiving it will not know what state is being coming. Quite remarkable. Now, how was the circuit for it? Very simple. As I promised to you. Now, two things I have introduced here called measurement. You see that the arrow fellow, that is measurement. So then I have used another object, control X, control Z. What is control X? Control X is actually your polymatrix 0, 1, 1, 0. Z is 1, 0, 0, minus 1. So you apply, if the measurement outcome is something, apply control X, something else, control Z. So this is the circuit which gives you teleportation. You can actually play around in IBM and do it. Now, for example, this is how my life started. There was a boy called Manu Gupta who sort of came and we were playing around in PRL trying to do something meaningful. First thing we asked is that if there's a Bell state inside your quantum computer, or for that matter, any entangled state. Now, entanglement is very tricky. Moment it is exposed, entanglement is gone. If somebody tries to disturb it, entanglement is gone. But then how do you know that quantum computer is working or not? If entanglement is gone, nothing will happen. So we try to find out that can you check without destroying it, entanglement is present or not. We took Bell's as example. As you can see, that there is an ancilla, something outside called ancilla. There are two ancilla. You can simplify it to one. That there are some using again same Hadamard control lot and measurement. You can actually check if the state is not there or not there. What do you check? You check parity. Is it 0011, 0110, or that is called parity. That, and the other one is sign, plus minus sign. Please check it out. That is indeed true that beginning you start with entangled state and the end of the measurement on the ancilla entangled state remains intact. Yet you know precisely what state it is. That's how I started my life. And unfortunately, this was verified experimentally by Professor Anil Kumar, and fortunately called it Gupta Panigrahi circuit. So there are things which you should keep in mind. For example, no cloning theorem, result from 1982, very beautiful paper. That a unknown quantum file cannot be cloned. So forget about cloning of this, SIP which was done in England. Unknown file cannot be teleported, cannot be cloned. But precisely what does it mean? That you cannot do it by unitary matrices. Whatever you cannot do by unitary matrices cannot be done fundamentally. Keep in mind unitary matrices. Okay, so as I promised you, very quickly I'll tell you some very recent work of ours, which was very during COVID period. We were playing around triple slit experiment. Yeah. This actually 2001 paper really motivated me. I heard talks from Professor Tabish Qureshi from Delhi many times about this kind of multi-slit experiment. Now, when I read this citation from his paper, what they found that the 3-slit thing, you put some problem at one slit, namely put a ground glass. Interestingly, the visibility increases on the other two. How can you disturb some point and yet visibility becomes better? And in the 3-slit kind of experiment, that actually rose my curiosity. So during COVID period, of course, students are there, and these are basically all of them are now doing PhD. Avinash is in Australia, Sydney, and Neha finished his PhD with Professor Tabish Qureshi, last author. Now she's a postdoc. Nitish is in USA doing his PhD, and I am here, retired from IISc Kolkata, back in Center for Quantum Science and Technology in SWA University. So what we showed is that very interestingly, three things get connected. One is which path, namely which slit it is going through, that information. Then coherence, which is responsible for visibility, and fortunately and interestingly, entanglement. The path get entangled, and they satisfy one exact identity called triality. Okay, very quickly, I'll just point out to you. Multi-slit experiment, to be precise, 3, more than that can be done. Visibility, namely fringe visibility. Path predictability, which channel it is going through, is it slit 1, slit 2, or slit 3? And which way information? Path distinguishability. There are precise measures for that. and all these things are actually measured, then which way information you will find out actually gets represented by entanglement, path entanglement. And amazingly, there are three terms, they add up to one. So I will quickly point out to you double slit experiment. Jack points out interference, so visibility, dark and bright fringes. Started from Young's double slit experiment, demonstrated wave nature of light. Dirac used it to show what is particle, what is wave. If you know exactly which slit it is going through, there is no interference. That means you know that it's a particle. Wave nature is gone. If you absolutely do not know which channel it goes through, then perfect visibility, wave particle duality. That's how you find. Now it is used for random number generation. Now from double slit, very basic idea, superposition psi1 plus psi2, mod square, find interference from psi1 star psi2 plus psi2 psi2 star of diagonal elements. That's called visibility. Quantum coherence, modern name. All right. So you can deal with it a bit more formally. So you can see that, instead of this is I represent by matrices, it was psi1, psi2. Now I represent matrices because I want to allow, less probability of going through channels. I put a number pi there. Okay. And it should represent the physical phenomena. So rho diagonal is equal to rho, trace rho is equal to 1. So you call it a density matrix. To qubit, expand in terms of polymatrices. So anyway, mathematics part is here, and there's a big history behind it. It started with the work of, again, Utos and Zurek, very foundationally, amazing people. And they pointed out, they analyzed Niels Bohr's question about wave particle duality concretely. They pointed out that visibility and which path. Okay, there is some precise connection. P square plus P square is less than equal to 1. Visibility is good old visibility, I max minus I min by I max plus I min. Then it pursued, then people came up with these things that, no, how about a path detector? Two path experiment, which way it is going to. So visibility is always there, V. Path detector or which path, accordingly you have P or D, always less than equal to 1. So now we follow this thing, multipath interference. Multipath interference brings in this subject called entanglement. So I will have to slightly modify it. Off diagonal elements, rho ij, that give rise to coherence. As I noted earlier, psi1 star psi2 plus psi2 star c1, that is coherence. Then comes, you have to find out your density matrix, can be in general complex. The phase you bring in there, and then try to put a detector to see which way it is going through. Detector will measure which path, D1 and D2, two detectors. And how do you put mathematics? Equation 8. Take a direct product state like Varnaman did. But finally, after you measure, the state will collapse. You have to take it out the detector. That's what you do. DJ decay. DJ decay, if they're orthogonal, then it is 0 or 1. So if it is, for example, if you through only one path, one of them will be 1, rest will collapse. So these are the simple things which comes in. You do it a bit carefully and incorporating the detector. And lo and behold, you can massage it, do it a bit more carefully, and all these things don't get into details. This paper is published. If some of you want, you can read it. Once you do all this massaging correctly, let me show you the end result. End result is that path distinguishability, which is essentially entanglement. Keep doing. And what do you find? What is the thing? Too many things here. Okay, so you reproduce the old results. And then finally you find that whatever is there, equation 28, that comes as entanglement. And entanglement is precisely in the way which we had, myself and Vineet Bhaskara had found, who was a student of IIT Guwahati at that time. And he exactly adds up to 1. So which path? Visibility and entanglement. Entanglement, there's a name for it now called eye concurrence, is precisely the area between vectors. Some of you which are curious, I'll give you the reference. This was recently verified. Where was it verified? Here, this is our published paper. And this Nature paper verified it. Universal conservation law governing the wave particle duality and quantum entanglement, February 2025. Just this February. Okay, quite interesting. You see equation, and this is the paper I was talking to you, generalized concurrence measure for faithful quantification of multipart pure state entanglement to Lagrange identity. It was pointed out to us that it is not Lagrange, it is actually Brahmagupta. And here is the paper which describes it in the continuous variable. So for continuous variable also you can do it. And I will stop it there. Just highlight for you this classic EPR paper. Beautiful paper, very readable, Bell's paper. And this is the Zeilinger going beyond Bell's theorem. Why do you need it? A lot of new things have come up now. Some of these things are, I'm talking about something called steering. People are still doing research on this steering. It was Schrodinger who came up with this idea. One of our key player, Arun Kumar Pati's name is here. You can check. Now people are talking about entangling qubit with microscopic object like a bacteria kind of thing. So people are now doing lots of things. Here is our one-day workshop on quantum, our foundation day. I am now with part of Center for Quantum Science and Technology in SWA University. So we have in Odisha, we have a group stepping up, and we have some large number of project students. This was the first picture was from IISR. Some of the students are from Nagaland and many other places, Northeast, Punjab, and things. So in ISO Kolkata, Mohanpur campus. This is in our campus here in Bhubaneswar. I'll thank you here. Thank you. I think I'll stop here. You can ask questions. Hello?
Thank you, sir.
Yeah.
Uh, so now we open the floor. So now we open the floor for questions and answers, for
Yeah.
questions and discussion.